Ne le, da v Ljubljani komaj čakamo odprtje plavalnega centra Ilirija, ki bo prav gotovo doprinesel urbanosti in pa tudi zdravemu slogu in srečevanju meščanov. Kolikor vem in kolikor sem se pogovarjala z arhitektom, glavnim arhitektom tega objekta, ta proces traja že skoraj 25 let od prvega razpisa, kar je bilo zanj nek tudi nov presežek, pa pustimo to ob strani. Slovenija sicer tudi počasi prebivalcem omogoča dih jemajoče razglede z vse večjega števila stolpnic. Ker se radi Slovenci učimo s primerov dobrih praks, pa vam bomo v nadaljevanju skozi prizmo naslednjih 2 primerov pokazali, kakšne pristope uporabljajo v nam zelo zgledni Švici. Prvi primer je športni in plavalni center Oerlikon v Zürichu, ki je zasnovan z mislijo na podnebju prijazno gradnjo, združitev bazenov in drsališč. Njegova odlika je energetska samozadostnost. Stolpi so zbiti zemlje in sicer shranjujejo energijo, medtem ko so solarni paneli na strehi, ki prispevajo k proizvodnji elektrike. Na drugi strani pa je primer lesene stolpnice imenovane cvat. Gre za kombinacijo lesa in betona in tudi drugih materialov, gre pa za idejo doseganja približno 20% manj ogljičnega odtisa. Oba projekta predstavljata nove standarde trajnostne arhitekture in energetske učinkovitosti. So, dear guests, I invite to the stage 2 experts, members of the management of the architectural studio Boltshauser Architekten, who perfectly combine innovation and sustainability through their works. These are architects Mr. Mark Inderbitzin and Mr. Matthias Stocker. Welcome to Slovenia. We are very much looking forward to your ideas and insight to current practices. So, welcome, dobrodošli na oder. Vam, spoštovani gostje, pa veliko užitka in veliko pomenljivosti ob predstavitvi 2 krasnih švicarskih primerov. Welcome. Hello. The stage is yours.
Good morning, everybody. Thank you very much to Andre and Violetta for this very warm welcome yesterday, and thank you very much for the invitation. We're very proud to be here to represent our studio, Boltshauser Architekten, at this convention. Like the miss before said, my name is Mark Inderbitzin. I'm in charge of a group of the executive board in Boltshauser Architekten. And I'm also in charge of the sports center of Oerlikon, which I was asked for to tell you something. Before I start with the sports center, I would rather take a little loop, a cascade on projects I would like to explain to you to end up at the end at the sports center, because everything adds up a little bit or leads to the results of the sports center. Since we are, for you to better understand the ways we think, we operate, we innovate, we create stuff and we design stuff, and we often do that around a specific material we're interested in since 20 years, and that's the material rammed earth. And I think we also do other projects, of course, but we have a few specific projects we did in this area with the rammed earth, and it might be interesting for you to look at this project from this material from a different view, also maybe as an alternative to concrete, since we are here in this environment. So let me start with the house Rauch. We did together with Martin Rauch, a well-known expert in rammed earth construction in Europe, also known as Bizet construction. That's the French expression for it. He asked us to collaborate in the year 2004 to 2008 on his very own house based in Austria, in Schlinz. It's a very beautiful site on a slope where the house is located, with trees, forests around. Very beautiful thing. And we also did already a few buildings in Zurich with rammed earth, and he is, as I said, he's an expert in it, and he wanted to collaborate in this building to set an example in a building built with an old tradition, with a very economic tradition originally, and also with a very sustainable tradition, to build a new house with modern expression, let's say. And the other goal was to use as much as excavation material on the site to build the house. At the end, we managed to do 80% of excavation material from site to build the house. Of course, not everything you can do with this material, glasses, wooden interior things, or doors, and some isolation stuff we couldn't do with this material, but we wanted to kind of show the world what can be done with a very sustainable technique nowadays. Everything was built on site. Here you see a slide of the excavation pit with all the formwork there is. It needs to be very strong. It's similar to concrete formwork. I don't go into details here at this point. Why am I telling you all this? Because it's a way, especially in this small house we did there, it's a really smart way to kind of take a shortcut in the circle of how the industry at the moment is working, because excavation material is usually considered as waste. So you dug out the hole, take the waste, bring it away, throw it away, basically, and then you bring new material to the site to build up the house. With this technique, and it's a quite ancient technique, of course, you probably all know that, you can use the actual material on site. So you cut off a lot of energy emissions that you expose through the cycle. You have the gold underneath your feet you can use to work with. And that, probably not telling you anything new, that has been done all over the world. You know the places, they're marked here on this map. The dark green places are areas which are rich in earth you can build houses with, and in all these places there are also buildings that still exist that you can look at. Here you see a section. Of course, we also took care about technical system in the building to keep it low-tech, everything. The rammed earth has a few very good advantages. For example, it can absorb a lot of humidity in the air. It can regulate the air climate very well, as it has this, and because you have to build in quite thick masses, it also can absorb temperature really very well and stack the temperature in the building. Yeah, I could on this point I could talk much more, but I want to get ahead a little bit. Of course, if you do a modern building with an ancient technique, you also need to reconsider certain details. For example, when you look at Chinese buildings that have built with rammed earth, they always had this really big roof covering the walls against erosion and again to protect it from the weather. We here invented new details with really low burnt rammed earth tiles that we put into the facade to protect the facade from erodating too fast. As one example, there are many other examples we invented. You can see here kind of a detailed axonometry drawing. Of course, you can do slabs, for example. This technique reacts only very well on vertical pressure, as you probably know. Then we also were experimenting with tiles with an old Japanese technique, the raku technique, and we developed these beautiful tiles. There's some pictures from the basement. You see some slabs there we did. Then there's the staircase that is connecting all the 3 floors together. I'm not showing you the floor plans right now. It's quite simple house, one family house. everything is isolated with, what's that called? I think reef, hold on a second, reed, also biological material, except the staircase. There we were keen to see how the staircase and the climate in the staircase reacts, because these walls had to be much thicker. Then all the surfaces in the interior are done by this excavation material we found on site. The floors, the walls, everything. And here another example of it. And we also did some statics. I show you two of them at the moment, together with the university in Lucerne, regarding relative humidity in the building. As I said before, the rammed earth has a very good capacity in hygroscopic hygroscopic abilities, and we always, with both statistics, we compared like a casual built house, single family house, to this house built in earth. And you see at these plots on the left diagram, the light green, light gray plots are the plots from the earth houses. They're pretty much quite stable in between a percentage of 60 to 40%, which people in houses feel as comfortable, whereas the other, like a conventional built house, has much more diverse spray. And on the right diagram, you see the diagram of the embodied energy, and we kind of proved, of course, these are always calculations, but now we pretty certain of how the feeling is in this house, because it's so old already. But we calculated that you have kind of a difference of almost 50% in embodied energy to a normal built house. From there on, I would like to take you to some things we do at the university, especially Boltshauser. He has been to different universities, mainly in Switzerland. For example, in Lausanne, the French part of Switzerland, but also in Zurich, and there we kind of followed the track on the rammed earth examples there are in Europe, because also in Europe it was a traditional way to construct, like before steel concrete got invented, like 160 years ago. It was quite a common tradition, especially in France, in the north and east part of France, around Lyon, but also in Switzerland. We discovered all this building, we made a book out of it, we combined it with the modern building and showed some details in the book. We did even, we put all the buildings on a map that people can look at them. We showed, like I said, different examples. And we also went into the Cointreau, that's an architect out of the 18th century that experimented, or kind of, he did a book at that time about the rammed earth building. And it's really interesting to see, I'm just showing you that because the foamwork he used was pre-concrete invention, and it's pretty much exactly the same when you look at the plans. With the students together, we did the one-to-one mock-up where we built up around the earth with this old technique, and you even see you got this climbing foamwork here already invented at that time. So in a way it's quite similar, but also it's not. So we went following him up, this Cointreau and all this old building, and we, of course, got to the solution that it's not. It might be a good solution for single-family houses, like we did for Martin Rauch, but it's not really possible to integrate it very well in the building industry we have nowadays. Nowadays, you have to build high, you have to build fast, you have to build cheap, and that's not really doable with the material, because if you use it on site and you do everything by hand, like we did the house Rauch, you're slow, So you're expensive because the people cost you a lot, and then you can't really go into high dimension with the pure issue. Just these diagrams I can skip. On the left side is how the building energy decreased, at least in Switzerland, by new technologies, better isolations, and so on. I think you heard that a lot in different lectures as well. And right is on the right side, it's the circle of how many greenhouse gas emissions the building industry produces, and just to show you the impact we can make in the future. But this you already know. So back to the traditional way of building. Then now we went to the universities and tried to evolve the learnings we got out of this traditional way of building. And one of the results for us for the future might be, of course, hybrid structures, also to combine all these good parts of the earth, the rammed earth, combine it with other materials and structures, and take like the best with both of it. So this was an example for the students to motivate them. This is a combination with steel, combination with wood, combination with concrete. And we did together with the students these mock-ups. We let invent them buildings that concepts that work, and let them build these mock-ups in one-to-one scale. It's really nice for the students because they can do something with their hands. They can work on something. Here's a hybrid with wood. One student did even a slab. He found out an idea of course, always with our help and with the help of engineers we have at the studios, to do a pre-tension slab with these wooden blocks between, and he even proved with his own weight that it's stable. And then we went on with the students. This happened in Lausanne. We went on with the students to do an actual project, a pavilion for an art fabric we have in Switzerland. They needed a pavilion for some sculptures they wanted to show. So we actually wanted to do that with the students. At the end, unfortunately, the money didn't, they didn't have enough money, so we just could do a one-to-one scale mock-up. So we organized summer schools together with the students, and they could participate in this. And we ended up with this mock-up, and that's actually kind of our first proof of this of a hybrid structure together with rammed earth. This wall is around almost 7 meters high, as far as I remember, and it's a combination between concrete and rammed earth. It's quite simple. You might know it already, or you have to know that rammed earth is very stable on vertical pressure, but not so stable on horizontal forces such as wind forces or earthquake forces. So the thing how to stabilize it is to put more pressure on the wall to make it more stable. And the way to do it is to pre-tension it. This you probably all know, of course. And this is exactly what we did with this mock-up. So we were really interested if it worked. Of course, we couldn't simulate an earthquake on this site. So, but we were keen in, we were really interested in how this pre-tension works, and at what point it stabilizes itself, because you also have to know that when you produce these walls and ram them, the material is humid or is moisted. It has like this moist or this Feuchtigkeit from the ground, and then it sticks better together and it dries out. And of course, if a material dries out, it uses its volume, and through the pressure also it compresses the whole thing. So it was logic that after a while you need to readjust the cables. So this we had to do twice, at the beginning and after a month, and then it became stable. So it was a proof for us that it works. And And then we went into a higher scale. As the project before we did with the students was kind of a pavilion, rather flat building, and then we got the imitation of a kiln, also of a brickwork museum, also in Switzerland, to do a tower for them. They wanted, on one hand, they wanted a tower to have a great view over the really nice area they're based in, but they also wanted a kiln, an oven to burn bricks, and they wanted an exhibition room. The kiln they wanted because they couldn't burn the bricks anymore for showing purposes, because this ancient house they're in, or the old house they did that in, it's part of the museum, is restricted in terms of fire safety, and this is why they wanted this this kiln. And then we invented this project also together with the student and added some new elements that we were interested on. One is the life cycle, of course, of a building, that you can decompose the building at the end of its lifetime. So everything is you can take everything apart at the end. Then we added the theme of prefabrication. Of course, it's also a well-known aspect, but it's of course in the rammed earth construction also better if you are able to prefabricate it. You save some time, you're faster. So we did that also in arrangement of summer schools, that the students could try it out. And then here you see the mock-ups where they prepared in the hall nearby, so we didn't have too much way to shift the material from one place to the other. You see some photos how it gets built together. Here is a section of the building. At the end you have this kiln, the oven where you can burn the bricks to educational purposes, and then you have the showroom on the floor. It's quite a high room, and then the view top on the rooftop. Here you see a picture of the outside. This time we used, instead of a concrete beam, we used a wood beam to tension everything together. You see here the elements, and the elements are divided by also this what we had in the house Rauch, this, we say it in German, drop noses to prevent the facade from the water, so the drops don't touch the wall. Exactly, this is a picture from the inside of the exhibition room. This is a detail plan again, and this is the kiln from the inside. This one we couldn't do with the rammed earth system. We had to do with bricks, and we did it with compressed earth bricks with a little amount of cement into it to make it more stable. It has to be more compressed, that it can resist the fire and the warmth and the heat from the oven. This is a picture from the outside. You see the tension cables a little more detailed. And also, of course, we did study how we did the project I showed before, how the tension reacts over the time. Then we went to another project where we combined as a hybrid structure steel with rammed earth. This, unfortunately, didn't get built. It was on a site in Rapperswil. It's also near Zürich. At the train station, and the use was a case study project at the beginning, but with the idea the national train company might build this house at the end. It didn't happen so far, but we're still hoping for it. Anyway, it was for housing and for offices, the purpose of the building. Oh. Excuse me. Yeah. Here you see a section and the floor plan, the core of the building, and also the dividing walls are made out of these thick rammed earth walls. You have a staircase at both ends of the building, and you can get to the apartments or the offices through balconies. And this is a model we did from the outside, and again you see here like the intention we developed a little further in terms of the steel. We tried to, of course, we would try to use recycled steel. Kind of that's also a theme very well discussed, you know, to close the circle of the lifetime of the materials. It would be recycled beams on the top, and for the slabs, I always forget this name, I'm not even sure if it's right, but the sheet pile walls, the walls you need to save the excavation pit when you dug out the building, you know. Maybe you see it a little better here. We would recycle those as well and fill it up with mass, also with, of course, rammed earth to get all the physical aspects the building needs. Of this, at least, we did a little scaled one-to-one mock-up to see if it's possible, how it functions in the process when you have to ram these sheet piles into a wall. Then, of course, we did studies with pictures. Here also that you get an impression of the building. And then we also got into the kind of the technical system of the building. We were like really interested to use the benefit of these thick walls also in the heating system, because we couldn't do a heating system bring a heating system into the floor, so we had to do it. We had to put it into the walls, but that's actually really nice because the walls are so thick, it can capture the temperature and give it to the room really slowly. It's nice. And then, of course, we work with solar panels on the rooftop to gather some energy. And then the idea was to do at the end of the building these two energy stack tanks, to integrate them together with the staircase we needed to get up, to collect energy in summertime, mainly in summertime, and stack it in this energy tanks to the building, which we combined with the staircases, and you can use further on when needed. And here you have an impression of a ceiling, how it could look like. Then another detailed scale of this energy system we were working on, and then an image of a balcony. Yeah. And then we're at the sports center, where a lot of these themes kind of end up and find its result in an actual bigger scale building. So we started at the Haus Rauch at the beginning, a really small building, more than 20 years ago. And now we end up with the biggest building the city of Zurich is currently planning. We won this project through a competition. In Switzerland, often these kind of projects are won through competitions. It's actually a really nice thing because it's good for the offices to compete against each other, to rise the standard a little bit. Anyway, yeah, it's around. It's located in Zurich, at the northern part of Zurich. There was already an existing ice skating rink on site, and also bathing center or swimming center. And the city evaluated the situation because it also could be good to preserve these buildings and to add new components. They at the end they came to the conclusion that it doesn't work out. If you sum up all the topics from sustainability to costs and everything, and to the program, the uses they wanted to fill in. We did it again after we won the project, because we want to be sure that it's really a smart thing to build a new house. Yeah, we're building a new house now, and you see on this lot on the north part, this white rectangle is the sports center, combining a lot of uses and sport activities because the city is growing quite fast for Swiss standards, and a lot of people want to do some sports and need for more attractions and activities they can do. On the south side of this slot is this changing room building for the football players. It's only for the football players. They can change it there. And then the area also contains 6 football fields on the ground and 1 football field on the roof of the building. That's how the main building looks like, the one on the north side. The city of Zurich was quite keen to make an example, said in German, light tower project. I don't know how to translate this, but an example in terms of architectural expression, of course. They want to make an example how smart it is to combine a lot of uses into one building, and they wanted to do an example in terms of sustainability for these kind of buildings, because in the core of these buildings, they're a huge waste of energy. Also you see it later on, and one can discuss if it makes sense to do this or to not do this, but yeah, we wouldn't probably get to an end. Anyway, also in the architectural expression, we want to kind of be bold and make also a statement. The whole building has the first 2 floors, the ground floor and the first floor, completely open with glass. You can walk around the building, you can look in and look out in every direction. That was quite important for us because the dimensions of the building are 120 meters. It's quite wide. It's a problem for daylight, so we open up the 2 first floors, and the most of the uses that need daylight are based there. And then you have this ring of this truss line material. It's comparable to the earth material we used before. It's a horizontal kind of horizontal element. Then you have this part between where's air, where's nothing. There's a fence, and we would like to do greenery on it, to plant a green facade on it, and then it ends on the top with the photovoltaic models we had to build as a ring around the building because there wasn't enough space for photovoltaic modules because we had already a football field on the roof. And then, quite iconic, we think, are the towers surrounding the building, the 10 towers, which hold this roof of the photovoltaic models, but also have inside, again, this energy stack cubes, cylinders, filled with water, and the fire escape stairs around them. This is the football building. I'm not going to talk about that too much. Of course, it has also a lot of PV around, and that's the floor plan of the building. Here. You enter from the south. You enter from the south, and then have a quite good view over the whole building and over the most important uses there are in. And you can, for example, you can see here, right to the whole building, to the end, to the end of the building, 100 meters long distance. If you stand here, you can also look through the building. That was quite important, as I said before. Then we have a diving tower pool up here. It has to be built for international contests. Then a 50-meter pool also for international contests and competitions. Then we have here a fun area where you have a warm pool, and then you have water slides, and you have pools for children, and then you have these educational pools for schools that can learn to swim, but yeah, clubs and other sports organizations can use them also. For example, water rugby, I didn't know that it existed, but it does. And then we have an area outside, the summer pool outside, and then we also have these ice hockey rinks stacked above each other. This one is the one on the ground floor, and then we have restaurants in the first floor and the second floor, wellness areas. We have two gymnastic halls in there, and so on. So a lot of things in there, and also a lot of different climates. We have kind of summer and winter in the building, and summer and winter outside, and all these issues with water we have to deal with, of course, and all this aggregate, in water, in ice, and in air we have to deal with. I tried to keep it short a little bit. I'm going to show you three essences of the building. One is for sure the primal structure of the building. We're trying to do as much as possible in wood, also in terms of sustainability, but we didn't do it just because wood is kind of the only solution. And of course, we have concrete in the building. We need concrete. It makes a lot of sense to use the concrete for certain purposes. But we tried also here to find a hybrid system to take like the best of both of each materials. And the thing I would like to show you a little bit are the beams we invented. We want to do them out of wood, also of glued laminated timber, and pre-tension them and bring it on site, either prefabricated or part of it fabricated on site. We're in the middle of the process. We don't know yet how we're going to do that and how much it costs. Because these beams are either the shortest ones are 20 meters long and the longest ones are 40 meters long. And that's quite a special way to do that with wood and also pre-tensioned. So to be sure, we did together with the city or for the city, and together with universities and testing centers, we did also studies and compared it to steel beams, to concrete beams, to wooden beams, and we did a matrix. We sorted kind of out which one is the best result, and we're certain that in terms of civic engineering, this works. We did some tests. We did one-to-one tests in laboratories to see. I don't know, something is wrong with the two pictures left, but the right one, you see it a little bit better. We did the test to be sure, and we also evaluated in terms of sustainability, which is the best one. We looked at the cost and everything, and now we want to do it. And it's not well known in building to do this kind of beams. Here you see the section. You see on the left side of the section, you see this stapled ice hockey rings. That's a really big challenge to do that because they have basically zero tolerances on the ice field. This are really, really, it's really critical, obviously, that you have good ice. It's 1 to 2,000 tolerance we have to fulfill there, because obviously the hockey players know if on one side the ice is 2 centimeters thicker than on the other side, because the puck gets lower, and that is a disadvantage during playing. So this is going to be a real big challenge for the beams over the ground floor. The other beams, we're quite certain they will work. Of course, there are issues we have to solve in terms of humidity, of water, corrosion in the bath, in the ice hockey hall. In both worlds, it's quite a big problem, or the challenge, I would say, This is a picture of the of the 50-meter swimming area. This is a picture of the diving tower area. Everything's quite high, quite long, quite big, and these beams are 2.60 m to 2.80 m high, 45 to 60 centimeter wide. Like I said, 40 meters long. It's going to be quite a challenge on the side to bring that in. Here you see the section on the upper section. I just wanted to show you the stapled ice hockey rings, and the rest is swimming area. Here another picture of the ice hockey rink on the basement. And then I jumped to the next theme, and that's the one I was kind of leading up to through the previous projects I showed you before. We also wanted to bring this architectural language into this building and prove ourselves and the world that it's possible to do this idea we kind of invented or reinvented or reused in this earth building at the beginning to bring in the bigger scale. You see here the towers are in this material. I have to say here it's now truss lime, but we started with this rammed earth material. And you have this horizontal architectural element. We want to do it in this material. We think it's really important to have, this, architecturally speaking, to have this balance between the massive elements, this iconic towers, corresponding to this more lightweight steel architectures with the photovoltaic roof, or the first two floors that are covered with windows. So for the material, we went on a search. I don't know how well you can see it. We went on a search with three different mixtures of materials. It started with a mixture purely out of rammed earth. And we did tests in laboratories in terms of all the civic engineering challenges it has to face, or it has to fulfill, and it's a big scale. You know it. You probably know it better than I do. That goes from water, from frozen points, how the material can erode. We did this one-to-one mock-up to test it, also on site. How much pressure it can contain in all different axes, and so on. A bit hard to explain in English. And then we always also did the research in terms of sustainability. And we did it. We started with the earth material. Then we did three materials where we mixed together the earth material with the truss lime material. Truss lime is more rigid, consistent in terms of stability. And then we did three mixers only with the truss lime and with concrete gravel. Also not concrete gravel, but gravel you need for the pumped concrete. I guess you know that. And we came out that in terms of embodied emission, that always comparing to concrete TEM 2, we're 30% better with the mixture at the end we choose. That's mixture 6, the mix between the gravel and the truss lime. And in terms of greenhouse gases, it's even 50% better if you compare this to directly. You see this on the scales a little bit. So the material that won at the end for the towers was the mixture of truss lime and gravel, and the one for the facade surrounding the building, this closed part of the facade, is the mixture between earth and truss calc, because it doesn't have to endure so much forces. The towers, as you see, are quite high. They're over 20 meters, and that's a scale we also have to be sure that it works at the end. That's why we decided on the other material that's more resistant. At the moment, we still have to pre-tension the whole tower. That's also not going to be that easy on site to construct that. this tower kind of leads me to the last topic I want to show you, and that's the technical building engineering inside, the heating system and all of that. That's also a really big issue to stay sustainable. I said at the beginning that's actually a little stupid to do these uses nowadays, because they eat up really a huge amount of energy. But if you combine the two uses activities, ice making and water heating together, you get a quite nice loop. So one can profit from the other by ice making kind of in our perpetuum mobile. Like in the loop is the idea, is kind of the heart of it all. And while we're making ice, there's a lot of heating that gets lost kind of and can be used to heat the pool. And our purpose or idea was to lose don't lose any energy out of the building and reuse all the energy. And the energy that's too much by producing ice, we kind of stack into this tower where we have this energy stack towers. You see that in the drawing in the tower, this capsule kind of thing. This is filled with water. The water is not directly filled into the lime truss tower, but it's a steel tank. You fill up, you can stack the energy in different energy levels and can reuse it, re-implement it into the building when you want to use it. And driven is the whole thing by electricity, of course. And the part of the electricity we try to produce for ourselves. This is why we built this huge roofs, PV model roofs, and the latest calculations are that we are able to produce at least 40% of the electricity we need to have for this building. And for example, here at the wardrobe building from the football players, we also operate with these roofs and need them also to give shade to the people who watch the football games and so on. So we're always trying to kind of infiltrate, combine like technical issues or issues from the client that has been ordered and architectural expression, and to mix it all together. That's a complete result. Here another picture from the facade, and here a short movie I would like to show you, and then. Yeah, that's it. Thank you very much.